First law of thermodynamics is nothing but the energy conservation principle. Energy conservation principle. Mathematically, the amount of heat exchange is equal, or more simply, if dq amount of heat be applied to a system, then it will increase some internal energy of the system and it will do some external work. This is the main statement of the first law of thermodynamics, where the first term represents the change of internal energy which takes place and the second term gives the external work done. Now, depending upon the sign of the work, that is dW, is either positive or negative. Depending on the sign, if it is positive, then some external work is done by the system, and if it is negative, then some external work will act on the system. Now, for hydrostatic system, dW is equal PdV for hydrostatic system. For magnetic system, this is equal to some minus of HdM. We will discuss later about that. Now, this is the main mathematical statement of the first law of thermodynamics, which is nothing but the energy conservation principle. If we notice the equation, then we will see that it is a combination of some inexact or exact differential, or more scientifically we can say that it is made up, or it is made up of some state variable and path variable. Now, which one is state variable and which one is path variable? The dW is path variable, dq is also path variable, whereas du is the state variable. So we say that dW is the path variable, dq is the path variable, and du is the state variable. Now, why dW is path variable? To explain this, we have to consider the following, or the adjacent figure. Suppose this is initial to this is final state. This is initial point and this is final point in the indicator diagram, PV indicator diagram. Suppose, what is indicator diagram? The diagram representing any two thermodynamic variable along two different axes. So we can join the initial and final state by different path, either this one or this one straight line, or some this line or this line. We will notice that the work is different for this path, different for this path, and different for this path, and different for this path. So work depends upon the path which we are interested. So work is path dependent function, whereas in case of internal energy, this variable it does not depend on the path. So this is a state variable, but depends only on the initial and final state. That is initial state this, final state this. So it is a state variable. So the first law of thermodynamics tells not more than that. Now applying this first law of thermodynamics, we can calculate the molar specific heat at constant volume and molar specific heat at constant pressure. If we rewrite the first law of thermodynamics, dq is equal to some du plus p dv. Now cv, what is cv? cv is nothing but dq dt at constant v. That is the amount of heat change. The amount of heat change per unit rise of temperature, keeping the volume constant. This is known as molar specific heat at constant volume. Now, to calculate this, we have to differentiate this partially with respect to t at constant v. Partially differentiating this, we get del u del t at constant v, and at constant v this term will get vanish, so there will be 0. So cv is simply, so cv we can write cv, we can write cv simply del u del t at constant v. Similarly, we can calculate the value of cp. We can calculate the value of cp. cp is del q del t at constant p, which is nothing but del u del t at constant p. Why? From first law of thermodynamics, plus p of del v del t at constant p. Now we can also get keeping dv constant, del p over del t, but p is constant, so del p is 0. Therefore only this term will get evolve and other terms will get vanish. So we get that cp is equal del u del t at constant p plus p into del v del t at constant p. Now if we calculate this again, if we simplify this, we get u plus of pv. Now what is this? This is nothing but the enthalpy of the system, H. This is nothing but the enthalpy of the system, H. So we can say that this is nothing but equal to del H del T at constant P. So Cp is equal del H del T at constant P, and Cv is equal del U del T at constant P. Now we can also calculate the difference between Cp and Cv. Cp minus Cv. We can get Cp minus Cv. Cp minus Cv is equal, what is the value? Cp is this and Cv is this. So Cp minus Cv will be Cp minus Cv will be del U del T at constant CV minus del H del T at constant P. But now we are interested, we have to consider internal energy U as a function of pressure and temperature. Then we get du equal to del U del T at constant P dt plus del U del P at constant T into dp. And if we consider U as a function of V and T, we get du del U del V at del U del V at constant T into dV plus del U del T at constant V into dt. So now dq is equal du plus dw, means dq plus dq equal to du plus pdv. Now putting this value, we get cp cv is equal cp is equal, putting this value we get cp is equal del u del t at constant v plus p into del v del t at constant p, and we also calculate the previous value, and putting this value in equation dq equal to du plus pdv, putting the value of du and dv, we will end up and differentiating with respect to t partially at constant p, we will get del u del t at constant v plus of some p into p plus del u del v at constant t plus into del v del t at constant p. Now cv is equal this, we see that cv is equal this, so cp minus cv means this term will get vanished, so only this term will be present. So putting this value, again we will see that internal energy U for ideal gas is the function of T only, so del U del V at constant T term will get vanished, so only we will let P into del V del T at constant P. Now we know that PV is equal at T, ideal gas equation, so del V del T is equal some R by P at constant P, so R by P. So putting this value we get P into R by P, P cancel out, so Cp minus Cv will be R. This is very important relation, this is known as the Meyer's relation. For n mole we'll get Cp minus Cv is nR. This is known as Meyer's relation. So these are some application of first law of thermodynamics, and the first law of thermodynamics is this.